First of all, this is joint work with Colin Ingalls and Paquette. And so I'm going to start with some motivation coming from the representation theory of finite-dimensional algebras, which is not at all my area of expertise, but I know that for some of you it is. So don't ask too many questions, but hopefully it will motivate some of the more geometric stuff that's going on later for people who were not already interested in geometric stuff. So then I'm going to move to the geometry. So I'm going to talk about moduli spaces of quiver representations and twisted sheaves on them. And then I'm going to give a construction of something called a quasi-universal sheaf on this moduli space. And then I'll return to the question of finite-dimensional algebras, and I'll explain the application, which is a construction of a generic brick. Okay, so here is some motivation. These are definitions that to many of you are familiar, but they were not familiar to me when I started this project. So this is for past Emily. So we start with a finite dimensional algebra A over a field K. And we say that the algebra is of infinite representation type if it admits infinitely many isomorphism classes of finite dimensional indecomposables. And a theorem, or here's a way to characterize infinite representation type using generic modules. So a generic module, I'm in this box over here. So we say that a module is generic if it satisfies these three properties. So first of all, it's indecomposable. Secondly, it's infinite dimensional over the field. But thirdly, that its length over the endomorphism, over its own endomorphism algebra is finite. And this is called generic. And it's a theorem of Crowley-Bovey that A is of infinite representation type if and only if it admits a generic module. So somehow if you have one generic module, you can use it to produce infinitely many finite dimensional indecomposables. Okay. Now we have something which is a little more specific than indecomposable, which is called a brick. So a module is a brick if its endomorphism, oh, I erased too much. Now I erased too much again. An A module is a brick if its endomorphism algebra is a division algebra. And we say that the algebra A is brick infinite if it admits infinitely many isomorphism classes of bricks, which are finite dimensional. So people are interested in this because maybe an algebra might have infinite representation type, but still have only finitely many bricks. So it's a way of controlling algebras of infinite representation type, which in general could be very scary, and these ones are slightly less crazy. And another reason, okay, this is the only thing I'm going to say about cluster algebras, is that it's a theorem that A is brick infinite if and only if it's cow tilting infinite. Okay, so we want basically a theorem that's analogous to this kind of picture for the brick story. So we make a definition of a generic brick. By we, I don't mean me, representation theorist, which is a generic module such that it has this extra condition that its endomorphism ring is a division algebra. And it's a conjecture due to Kaveh Moussavan and Charles Paquette that A is brick infinite if and only if it admits a generic brick. So as evidence, for example, this is known for hereditary algebras. But the problem that they're having is that in general, they don't know how to construct generic bricks. So they can't find either examples or counterexamples of their theorem beyond the hereditary case. And so this is the story that Charles was telling at some talk that Colin was at. And towards the end, Charles made a comment that if the moduli space of representations for a quiver had a universal sheaf, universal module, then maybe he could work on this problem. But we know that it doesn't. There aren't universal sheaves. And so he couldn't follow that approach, he thought. But Colin, who knew about twisted sheaves, thought that perhaps we can use that to build a quasi-universal sheaf, and maybe that's good enough. And so that's how this project started. So that the original motivation really comes from finite dimensional algebras, but then now we're just going to do some geometry for a while. Before I move on, are there any questions about that? Yes.
about just the problem that's labeled there.
Yeah.
And so in the theorem of Crowley-Bovee,
Yeah.
so what they use is this sheet you're describing to construct those generic modules in the case where the algebra is representation infinite, or how does?
I don't know.
Okay.
I don't. Yeah.
Because
good question.
Like
yeah.
It's the construction underlying this theorem, which they're trying to mimic on the other side.
Right.
The brick infinite
Yeah, I'm not sure like how close of a parallel. They don't. The proof is not going to be the same.
Okay.
Yeah.
And another question. So for a generic brick, does the angle length coincide with the dimension over, what's like vector space over?
That's another good question. I don't know. Does anyone know? Again, this is not my area. I like sheaves. Okay, so here comes a variety. So we can talk about sheaves. So let's establish some notation. As I said, we're going to build a moduli space M, and I want to use M and its geometry to construct generic bricks. And why should I talk about quivers? So let's just recall that any finite dimensional algebra A is equivalent to a quotient of a path algebra for a finite connected quiver and by an admissible ideal. And for now, for this talk, we're just going to assume that our algebra A is the path algebra of an acyclic quiver Q with vertices Q0 and arrows Q1. I drew an example there of a quiver, and I'm going to fix a dimension vector D.
So for if it's just a path algebra quiver, is it brick infinite or?
We will see very soon that there is a strong connection. Yeah. So what's a representation of this quiver? The idea is that I put some vector spaces of dimension di at each of my vertices, and then I put some matrices in between. So that's the picture, and then we have a more formal definition here. And now I want to know when two morphisms or two such collections of matrices should be considered isomorphic. And so we have an action of this group G, which is GLDI, which is changing the bases on each of my vertices. And so that's acting on R. But inside of G, I have a copy of GM, which is given by a bunch of diagonal matrices. And when we conjugate by a diagonal matrix, we do nothing. So this group, which I'm going to call delta for diagonal, it acts trivially. And that means that the action factors through a group which we'll call P, which is G mod the diagonal. So it's kind of like P is supposed to remind us of PGLN. Okay. And so now using this notion of objects and morphisms, we can define a moduli space. So we fix a stability condition. I'm not going to talk too much about that. But inside of this set R of all these collections of matrices, I have some stable ones. Can I move my mouse? Yes, I can. And the key property for us is that the stabilizer in G of a stable representation is just delta, which means that P is acting freely. And so what I can do is I can form two quotients. I can form a quotient of RS. This is like a stacky quotient by the whole group G. I'll denote that by curly M. And that's the moduli stack of stable representations. But if I want a variety, I should quotient by the free action of P. And I denote that by M. Okay, probably I should have like an MS everywhere, but there will only ever be stable representations in this talk. And so curly M is a GM gerb over straight M. For those who like that, for those who don't, it's not important. Okay, and the remark that is related to Joel's question is that if V is stable, its endomorphism ring is the field K, and so V is a brick. And so in particular, if the dimension of M is at least 1, then the path algebra is brick infinite. Okay. And so if our conjecture, Charles' conjecture and Cave's conjecture is that that KQ is brick infinite if and only if it admits a generic brick, then there should be something about if we have dimension M at least 1, then we expect to be able to produce a generic brick.
Sorry, why the dimension M is 1 and it's brick infinite?
Because every point in the representation, every point in M corresponds to a brick. So if the dimension is at least 1, I have, and my field is infinite, then I have infinitely many points in the moduli space. So it is possible that maybe I could have dimension 0 and still have infinitely many like discrete components. So we don't have anything to say about that situation. But if there's a curve inside of M, we expect to produce a generic brick. Did that answer the question? Okay. Okay, so now let's talk about universal bundles, which is what Shah was hoping for. So what would a universal bundle be? It would be a sheaf on M, so it's a sheaf of OM modules, but we also want a compatible KQ action. So it's a sheaf of modules over this algebra, such that for any representation, V, if I look at the fiber of U, my sheaf over the class of V, that I recover V as a KQ module. Unfortunately, we know by work of King that such a thing exists when the GCD of the dimension vector is 1, and in general, it doesn't exist. So, but what we will show in this project is that we can find something which is quasi-universal, and we argue that that's good enough. So that's the goal from now on. And the tool for constructing a quasi-universal bundle will be something called twisted sheaves. Are there any questions before I talk about twisted sheaves? So as motivation, let me remind you some things about ordinary sheaves. So I'm starting with an étale cover of a variety M. So for us, often M will be the moduli space, but it could be any variety. And Y is anything living over it. And I'm just going to fix this notation. So I'm interested in the self-intersection of Y with itself. So I'm gluing things together on overlaps of the cover. And I'll call P1 and P2 the two projections. And then I have triple overlaps. And I'll use Q1, Q2, Q3 to denote the projections onto single factors, and Q1, 2 to denote the projections onto 2 factors at a time, and so on. So if I had a sheaf on M, let's call it F0, I could pull that sheaf back along U and get a sheaf on Y, and I would also get some extra stuff that we learn about in our algebraic geometry course. So let's call it F, the pullback. And if I pull back further to Y cross Y, now I have like a commutative diamond over here. And so I can pull back U and P1 or U and P2, and that gives me the same result. So I have an isomorphism phi from the P2 pullback to the P1 pullback. And that isomorphism satisfies a cocycle condition, which looks like this. Okay, so if I pull back further, I end up on my third copy of Y, and I got there in 2 ways. One is by pulling back along Q1, 3, Q2, 3. So I have a diagram like this that commutes, and as an equation, it's this condition star here, right? So this is the cocycle condition. And the definition is that this pair of F and phi satisfying the condition star is called descent data for F0. And it's a theorem that there's an equivalence between descent data, F and phi, when I vary my cover, and sheaves on M. I didn't need to erase this next box yet. Okay, so that's what an ordinary sheaf is, and we can access it through its descent data. And then the idea of Andrei Calderaru is to introduce a 2-cocycle. So this is a function alpha on the threefold product of Y, and say that an alpha twisted sheaf is given by a pair F and phi, such that the condition star is not exactly satisfied. So I've got F, I've got phi exactly as before, but the condition here has been twisted by alpha. And so in particular, when alpha is equal to 1, the constant function 1, we just get an ordinary sheaf. We get ordinary descent data, and then according to this theorem, we get an ordinary sheaf. So this is a generalization of sheaves on M. They're alpha twisted sheaves. So here, I mean, I've made a choice of cover, so that's kind of built in. But I can vary my cover, I can vary my cocycle, and get different families of twisted sheaves. And they have some interesting properties that if I have a pair f and phi, which is alpha twisted, and g and psi, which is beta twisted, defined over y, I can take the tensor product of f and g, and I would be able to use phi and psi to define a morphism like this from the two pullbacks. But when I look at this condition here, I would get two factors. I would get an alpha and a beta. So the tensor product of alpha and beta twisted sheaves is alpha times beta twisted. And in particular, well, if I have a sheaf which is alpha twisted and locally free, its dual is alpha inverse twisted. And the tensor product of that thing with itself is therefore twisted by alpha times alpha inverse, which is equal to 1. And so this is a sheaf on Y, which satisfies descent and therefore corresponds to an actual sheaf on M. So this is a way of taking twisted sheaves and producing real sheaves at the cost of getting bigger, right? Are there any questions about that? So let me give some interpretation of twisted sheaves, because although this was introduced by Calderaro, he could compare it to a lot of things that had already been studied before this. So let's assume that I have an étal cover and a locally free alpha twisted sheaf. And so remember that that means that I have this phi from P2 upper star of E to P1 upper star of E, which satisfies this twisted cocycle condition. Then if I projectivize, my factor goes away because I no longer care about scalars, right? And so what that says is that the projective bundle associated to the sheaf E is a real bundle on M. So from a twisted sheaf, which is actually only a sheaf on Y, it doesn't quite descend to M, but its projectivization does descend to M. And then, okay, so here's some cohomology. This got kind of small. There we go. So here's part of our long exact sequence. Here's the connecting homomorphism. Here I have the class of my principal bundle. It corresponds to alpha in H2, the cocycle. And so we can see that this projective bundle will lift to an ordinary bundle if and only if alpha is trivial. Happened here. Okay. But lots of projective bundles do not really come from ordinary bundles. What they come from is twisted sheaves. Okay. And then we can say that there's actually a comparison that an alpha twisted sheaf on M corresponds to an actual sheaf on the total space of this projective bundle. And if I look at all the sheaves on this projective bundle with certain properties along the fibers, those also correspond to alpha twisted sheaves. So there's another way to think about alpha twisted sheaves.
Sorry, what was Y in that example?
Anything. Like I started with an étal cover, and E was alpha twisted over that. But it is kind of interesting that I made a choice of E here to define this thing, and then all alpha twisted sheaves correspond to that E. But you could have started with a different locally free alpha twisted sheaf and get a different defined over a different cover, say. Okay, another approach is through Azumaya algebras. So as we said, yes.
So back to that example. So if you pick any projective vector bundle, can you find the Y for which it is coming from a sheaf on phi?
Yeah. Because you'll just start writing down conditions like this. And then you'll see that locally you can solve them. Yeah. Okay, so as we saw, if we tensor E with its dual, well, that's the same as the endomorphism sheaf, and we saw that it's always one twisted, and so it descends to an ordinary sheaf on M, and that sheaf is a sheaf of algebras, because we have this endomorphism structure we can compose. This is a sheaf of, it's an Azumaya algebra, and we can also say that alpha twisted sheaves, F and phi, are equivalent to sheaves of A modules on M, and I can actually write down the functor, which says I take F, this was alpha twisted, I tensor with E dual, now it's one twisted, so it descends. I've drawn an overline to represent the descended guy. And a last perspective, again, these are not all important. You don't need to like all of them but it might give different people a different way to approach this definition, which maybe seems kind of contrived at first. So recall or learn for people who don't like gerbs that if you have a 2 cocycle, you can build a gerb. I've called it M alpha over M. And the fact that my cocycle was defined over Y means that when I pull back my gerb to Y, it's going to be a trivial gerb. So it's going to look like Y cross point mod GM. And that means that if I had a sheaf on curly M alpha and I pulled it back, I would get a sheaf on Y with a GM action. And it turns out that alpha twisted sheaves are equivalent to sheaves on M alpha whose GM action is of weight 1. Well, that's another way to think about alpha twisted sheaves. Are there any questions about any of this? Again, it's not essential for the following. So just different ways to think about the same kind of objects. Okay, so now our goal is to build a twisted sheaf on M. Here, M is back to being our moduli space of stable representations. So remember that that's the quotient of RS by this group P. And we want this sheaf to be universal or as close to universal as it can be. And so for this, we're just following some arguments of Mukai and Calderaro for moduli spaces of vector bundles on a curve. Okay, so the 2 key observations are first, that RS does admit a universal bundle. Okay, the quotient might not, but the guy before we quotiented did. There was no problem. It was an affine space. And that it's a principal P bundle over the base. So here's our universal bundle. I've called it U of RS. And what I do is I just take a bunch of copies of the structure sheaf according to my dimension vector. And I put them at each vertex. And then I have a tautological KQ module structure. So what I would like is for this thing to descend. And so when would a bundle over the total space descend to the base? It would descend if and only if it were P equivariant. Okay. But it's not. It's G equivariant. But this delta, this diagonal, acts with weight -1 and not 0. -1 is because of right-left conventions. If you have the opposite for me, you'll think it's 1. But we all agree that it's not 0. And so we don't have a P action. We just have a G action, and we can't descend. And so this is when Mukai tells us how to fix it. And he says, well, let's take a cover. And you'll notice I'm using the same kind of notation for my cover that I did before. But here, what this cover does is I want to trivialize this principal bundle. Okay, so I want that I have a Cartesian diagram like this, where I have the trivial P bundle over Y. And I've just given names V to the projection upstairs and U down here. And this trivialization is equivalent to having a section, sigma, from Y into the total space. Okay. And so what can I do over here? I can observe that on this total space Y cross P of my trivial bundle, I have 2 G equivariant sheaves. I have the pullback of the universal guy. It still has weight -1. But I also have a line bundle corresponding to the fact that I have Y times G over Y times P. And that has weight 1. Okay? So if I tensor these 2 things together, I get something of weight 0. And that does descend to Y. And so I call that UY. And it's still universal, because if I tensor a universal thing by a line bundle, it's still universal. Okay, so I do have a universal bundle on Y. I wanted a universal bundle on M. And I'm not going to get one, but what we're going to show is that this thing is twisted over Y. So how do I do that? Well, I use the fact that it's universal to say, if I pull back along P2 and P1, I should have some isomorphism between those things. Let's call that phi. And now let's check, does phi satisfy the cocycle condition over Y3? Okay. Well, over Y3, I get something, some composition. This is going around that whole loop of my cocycle condition. And if it was really going to descend, it would be 1. I can't say that it's 1, but I can say, well, it is an automorphism of a family of stable bundles. And we don't have interesting automorphisms for stable bundles. So it's at least a scalar. Okay. So this composition here is multiplication by some alpha, and then we can just do a quick check that this alpha is a cocycle. Okay. And so the conclusion is that the pair of uy and this map phi is an alpha twisted sheaf. Okay. And it is universal over y. Are there questions?
There's some explicit description of why.
In examples, we can say, I'll give an example later.
What are the fibers in map y become?
Yeah, it depends on the dimension, but I'll give a concrete example later where we're just like adjoining a square root of a determinant. It's like a degree 2 cover. Any other questions? Okay. So what do we have so far? We have an alpha twisted sheaf, which is universal over this total space, this cover Y. And I want to produce a real sheaf on M. Right? And well, what we've observed is that what I should do is I should find an alpha inverse twisted sheaf of some rank n. And I should tensor it with my universal guy, and it will be one twisted, and therefore it will descend. But I've ruined universality by doing this, right? So what will happen to my descended guy if I look at its fiber over some point corresponding to an isomorphism class of representations, its fiber will be the fiber of uy, which is v, tensored with the fiber of e, which is kn. So it's going to be a direct sum of n copies of v instead of v. And this is the definition of a quasi-universal bundle. It's just a thing that gives you copies of what you wanted instead of what you really wanted. And so a goal for us is to minimize n. Maybe we can't get 1, but it would be nice if we get something small, because an observation is that if I take a quasi-universal guy and take its direct sum with itself, it will still be quasi-universal. So we want to minimize the redundancy. And so here are some ideas for how we can do that. First, I need some notation. Remember that d with an underline was our dimension vector, and I'm going to write little d for its GCD. I'm going to write capital D for the sum of the di's, which is the rank of uy just as a vector bundle. And I'm going to write di0 for the minimum of the di's. So the naive candidate, the thing that we saw early on was that, well, if I have a thing which is free, which uy is, I can just take its dual. Okay? And I can always tensor it with its dual, and that will always work. But this is really big, right? So now my n, the rank that I've got too big by, is the sum of all the di's. So it works, but it's a bit disappointing. And an observation we can make to do a bit better is that actually each of the summands, so let's call it I at the vertex I, is of rank di, and it's also alpha twisted. So let's take the smallest summand and use that one. So that also always works, and now we've made n equal to the minimum of the di's. This is an improvement, but our goal and what we kind of came in hoping for was that we could make it equal to d. And that would be consistent with the observation that when d is equal to 1, we don't need this twisting business. We just get an actual sheaf, which is actually universal. So a lemma is that I can always choose alpha, my cocycle, to have values in d roots of unity. And so as a corollary, we recover this result of King, which is that if d is equal to 1, alpha has roots in first roots of unity, which means that alpha is 1, right? And so it descends, and we get a universal sheaf, just like King said we should. And another result coming from results about H2 of a curve is that if I have any irreducible smooth curve inside of M, so if M is one-dimensional, then I can always find an E of rank D that works just over that curve. So it's not universal over the whole family, but I can find a one-dimensional family of representations where I can get my E, and then my rank, my extra rank is indeed the minimal value of D. So we'd like to do it everywhere, but we can do this, and this would be enough for our construction of a generic brick if that's all that we care about. Okay, are there questions about that?
What's the reason for trying to minimize it?
Well, we want the endomorphism ring to be Eventually, we want it to be a division algebra. And if we have too many copies of something, then it's going to be block diagonal, and we're going to get a matrix ring. So, yeah. And also just, it seems like it would be more elegant to be more minimal. I think at this stage, if we just care about Charles' application, we have enough. Like we can stop with this, and we're happy. Okay, here's another construction that relates to projective bundles. So this is following some ideas of Ingalls and Reineke, who constructed a smooth model, they say, of the moduli spaces. So our input is Q and D and our stability condition. So like here's an example of Q. And then they have one more piece of input, which is that we add an extra vector. Here, we add an extra vertex at infinity. I mean, they say it doesn't mean anything special, infinity. It's just not any of the ones we had before. And we add EI arrows from infinity to I for each I. And then we look at a new quiver, Q hat, where we've added this vertex and these arrows. We look at a new dimension vector where we put dimension 1 at this infinity, and we have a new stability condition where epsilon is some small positive parameter. And the result, they tell us, is that we get a moduli space M hat, depending on E, over M, whose fibers are projective of this rank, the product of E times D minus 1. And projective bundles are related to twisted sheaves. So this is the first clue that something is going on in twisted sheaf land. And so our favorite examples are just where we add one arrow pointing to the vertex J, and we get M hat with fibers P to the dimension dj minus 1. And our second favorite example is where we add one arrow to everything, and we get P of dimension d minus 1, where d again is the sum of all the di's. And so if we compare this construction to our universal sheaf, the theorem is that this M1, the big guy, is the projectivization of our quasi-universal sheaf, or twisted guy. And the M delta J's are the projectivizations of each of its factors. So it's just a geometric way to recover Mukai's sheaf construction more from projective bundles. Okay, and then there's something about a germ, but I'll skip that for time. How much time do I have, by the way? I have 10 minutes, something like that. Okay, yeah. 10 minutes. Okay, so here's an example. As promised, it's for this quiver with 2 vertices and 3 arrows, and D is equal to 2, 2. So a sad thing about this example, which we understand really well, is that the minimum is equal to the GCD. So we can't tell the difference between the thing that we know we can prove and the thing that we want to prove. But the nice thing about this condition that lots of people have studied this quiver is that there's different ways to think about the moduli space. And one is using quadratic forms. So notice that from my 3 matrices A, B, C, I can invent 3 new variables, x, y, and z, and I can build a quadratic form, Q, which is the determinant of x times A plus y times B plus z times C. And it's some matrix X, which is going to be symmetric, 3 by 3 matrix. And the fact is that the pair ABC was stable if and only if the determinant of X is non-zero. And furthermore, if I simultaneously conjugate A, B, and C, then I simultaneously conjugate X. And so then when I take my determinant, I just get a scalar. And so M is, we can view it as the moduli space of matrices, symmetric matrices with non-zero determinant modulo a scalar. And so this is P5, where we've thrown away the thing with determinant 0. And so this is our M. And here I can define my quasi-universal sheaf using either the 2 methods that we talked about before, or I can just like do it by hand, which is what Colin did at the beginning. And so he says, okay, let's look at this sheaf of Clifford algebras on M, which has generators E1, E2, E3, but this relation EI EJ plus EJ EI is equal to 2 XIJ, where XIJ depends on the matrix. So it's going to change as we move around in the moduli space. So this is graded. If we put the degree of each of the generators equal to 1, and then we can split it into an even part and an odd part, and it's of rank 8. So A0 has 4 dimensions and A1 has 4 dimensions. And then I can write down my sheaf of KQ modules, which is this guy. So A0 is my source, A1 is my target, and multiplication by EI goes from one to the other. Okay. And so notice that this is twice as big as what we want, right? I wanted something with dimension 2 and dimension 2, and I have something with dimension 4 and dimension 4. And this is exactly where I can't get universal. This is the best I can do, but locally I can split. So I'm going to need to adjoin a square root. And so this is how the cover would come in. So let's just look for now over the locus where x11 is 1 and the minors are non-zero, and I choose a square root of minus the determinant. And what this allows me to do is write down this formula for f. It's some element, but the key fact about this element is that it's idempotent and even. And that means that it allows me to split the fiber of A at this point x into AF and A times 1 minus F. But I could only do that splitting after choosing delta. And then one can just check. I can write down a basis for AX0 of F and AX1 of F, or of 1 minus F. I can write down the matrices like our first year linear algebra students do for E1, E2, E3. And I can take the determinant, and I see that I get something which is isomorphic to ABC. Okay. And so what that means is that AX is a direct sum of 2 copies of the original representation, and A is quasi-universal. But again, we don't know whether this 2 is the minimum or the GCD because they're the same. So let me return, now that we have our quasi-universal sheaf, to generic bricks. So our conjecture is that if the dimension of M is at least 1, and U is a minimal quasi-universal sheaf, so we've minimized this dimension, then if we look at it over the generic point, so we tensor with the function field, then we claim that that's a generic brick for the path algebra. And a remark is that this is consistent with the observation that we made early on, that when the dimension is at least 1, we expect KQ to be brick infinite. Or we know that KQ is brick infinite. Okay, so let me remark on the proof. So we have this list of conditions we have to check, and we can see where the adjectives are important. So we need that the dimension of the dimension of M is at least 1, because that tells us that the function field is interesting, or interesting functions, and so we get right away that the dimension of this module as a vector space is infinite. We need minimality, as I said in response to Joel's question, to ensure that this module that we get is indecomposable. Because if it was 2 copies of something that I shouldn't have taken to begin with, then I should break that apart now and just take an indecomposable part of it. And the last part that's proving tricky for us is to show that this thing is a division algebra. So at first, Colin and I were very happy because in conversations, we always just talked about the endomorphism algebra. But it turns out we realized at some stage that Colin and I, because we were thinking about sheaves, we're always talking about the endomorphism algebra of this thing as a sheaf. And Charles was talking about the endomorphism algebra of this thing as a KQ module. And it's easy to show that the endomorphism module of this thing as a sheaf is a division algebra. But what we claim, after doing lots of examples, is that actually things which are KQ linear turn out to automatically be linear over the function field already. So at first we thought there's no way this should be true, but it works in the examples. Okay. And so if this claim is true, then that gives us a positive answer to part 3 as well. And so how do we do this not in examples? Well, we have a proof for a generalized Kronecker quiver. So that's a quiver with 2 vertices and n arrows. Okay. And it uses the theory of generic matrix rings. And so somehow this is saying that commuting with the arrows is enough to commute with the function field. Okay, but not everything is a generalized Kronecker quiver. But we do have this paper of Schofield, who proves that any moduli space of quiver representations is birational to a moduli space with a generalized Kronecker quiver. So that's great, but what we don't understand yet and what we're working on is what happens to the universal sheaf under this birational equivalence. Because, okay, a sheaf goes to a sheaf, that's great, but one sheaf was a KQ module and the other sheaf is a KQ prime module. So what properties are preserved when we change the path algebra under this birational equivalence? So that's what we're working on to answer this final question. And then in future work, well, as I said at the beginning, we're interested not just in path algebras, but in quotients of path algebras. So we need to look at the part of the moduli space that corresponds to representation satisfying this condition. And then, I mean, probably doesn't have applications to finite dimensional algebras, but we think that the story should work over any sheaf of finite dimensional algebras over any base x, so not just over a point. And so that is the next plan. And that's all. Thank you.
Can you use this to actually find bricks? Or?
We have to ask, well, this is a generic brick is a brick,
yeah,
but it's not a finite dimensional brick. But I think that this is known to people who, yeah.
It was generic brick implies brick infinite, right?
That's the conjecture.
Okay.
Yeah, it's not a theorem.
Okay.
So, yeah.
Because if you knew how to take a generic brick
Yeah.
and produce bricks,
Right.
that would like.
Yeah. Right. Yeah.
Yeah, so, with infinite representation type, you can divide things into 10.
Uh-huh.
So does this like tell you anything about when calling for some coming?
Not that I know of, but I'm not the algebra end of this project. No.
Thank you. Let's think I'm late again.